Alright, this is a kind of an extension off of piecewise functions, so I'm going to do a few application problems and then look at some graphs at the end. So go ahead and read the question. You just ordered something online and wanted to calculate the shipping cost. Write a piecewise function to show the shipping cost. So piecewise function means pieces or different pieces of functions that will encompass all of this information. So looking here, you know, they're going to charge you $6 in shipping for anything you purchase between $0 and $50. And then from 50 to 100, they're going to charge you $8. 100 and over, they're going to charge you $10. So your shipping cost is obviously dependent on the dollar amount that you purchase. So your shipping cost is kind of like your function value. And then your dollar amount is kind of like your X, like your domain. So when you write this, f of x is your function, and that's going to equal three different things. So you write your bracket, it could equal $6, it could equal $8, but it could also equal $10. And then, so okay, again, this is your actual function pieces, like what could happen at different x values. Well, then you have to give their specific domain values that occur at that function. So for $6, my domain has to be from 0 to 50. So I would write that x is anything from 0 through 50. And for $8, it has to be anything greater than 50, but not inclusive of 50, and then less than or equal to 100. And then for the $10 shipping charge, it has to be anything over $100, not inclusive of 100. And be careful with the overlap. Like here I include 100, here I don't, right? Or if you wanted to round to a penny like they did here, that would be totally fine too. So your domain is everything from $0 to technically infinite amount of dollars because it's 100 and over. So your domain is x is greater than or equal to $0, anything beyond 0, right? And your range, depending on what your domain is going to be 6 or 8 or 10. But again, don't write everything from 6 through 10 because that doesn't include $7, that doesn't include $8.10, and etc., etc. So here's your piecewise function and your domain and range based off of that. Alright, the good old airplane problem. First of all, this one is tricky, so don't be alarmed if you have to watch this more than once. So the problem says a plane descends from 5,000 feet at 250 feet per minute for 6 minutes. Over the next 8 minutes, it descends at 150 feet per minute. So it has two different rates. So for example, the plane is going to go 250 feet per minute, descending 250 feet per minute for 6 minutes. Then it's going to change its descension rate to 150 feet per minute, and that's going to be for the next 8 minutes. So from like 0 to 6, and then from 7 through 15 if you like. So obviously it's a piecewise function. Since I have two different rates, I'm going to have two different functions that are dependent on different domains, in this case time. So it says write a piecewise function for the altitude in terms of the time. So how high is the plane depending on how much time it's been in the air. So the first one is fairly straightforward. So altitude, I'm going to write, not so sloppily, sorry. Altitude, so a sub t, which is the altitude of the plane, depending on the time, is going to have two specific possibilities. So I'm going to start with this one. It's starting at 5,000 feet, so that's like your y-intercept, and then it's descending, so minus 250 t. And then that's only for a specific time. I'm just going to write this a little bit smaller. So minus 200, and it's minus, of course, because you're descending, right? So 250 times time. Well, your time has to be something between 0 and 6 minutes, because it says it's going to descend 250 up through 6 minutes. So there's your domain, and then there's going to be your function that you use for that specific domain. Well, then over the next 8 minutes, it's going to descend at 150 feet per minute. But what's tricky about it is once you hit this different descension rate, how high are you in the air? So now you have to think, okay, if I use this function and go all the way to the 6th minute, that's going to give me the height of the airplane before it switches over to this descension rate. So let me say this again. At the 6th minute, if I put 6 into this function, that's going to give me the height at the end of this function and at the start of the new descension rate. So if I take my original function 5,000 minus 250 times the 6th and final minute of that first function, I get 3,500 feet. Okay, so that's my altitude at 6 minutes. So now the second function is going to be at 3,500 feet, and then I'm descending at 150 feet per second, but now it's not times time because this time has to be subtracted from 6. So for example, if you were in the air for 10 minutes, 6 of the first 6 minutes would be here, and then the next 4 minutes would be here, right? So time minus 6 or 10 minus 6 to get that 4. And then this time is anything beyond 6 minutes, or technically, you know, the next 8 minutes, but that's fine. I don't think I'd be too picky about that. So there's your 2 parts for your function, and then it says what is the plane's altitude after 12 minutes? So 12 minutes, does it fit in between 0 and 6? Obviously not, so I'm not going to put 12 into the blue chunk. 12 fits into here, it's greater than 6, so I'm going to put 12 into the red chunk. So altitude at 12 minutes will be 3,500 minus 150 times 12 minus 6, which is obviously 6, right? So that's 3,500 minus 150 times 6, and you dump that in your calculator, and you get 2,600, and I don't have enough room here, but that's in feet. So again, spend some time on this problem and make sure you kind of digest the pieces. It's not the easiest problem. Okay, these questions say write equations for the piecewise function shown. So I'm going to scoot this up here. Okay, and I am actually going to start with the filled in circle. So what you need to do for these, this line right here, if I go past the filled in circle, I mean it's just a nice linear line, as is this one, just a nice linear line. However, it's 2 pieces, so 2 different lines, different slopes, different y-intercepts. So when you write your equation, you're going to have 2 pieces for specific domains. So I'm going to start with, let's just call this first one number 1, and I'll refer to that as number 1. So if I continue this line, not that I'm going to, but can you see that the slope, like if I go from here to here, up 1 to the right 1, up 1 to the right 1, up 1 to the right 1. So if I kept going up 1 to the right 1, it would have a y-intercept at 2. Not that I'm going to keep going, but I need to write an equation for that line. So that slope up 1 over 1 is obviously 1x, plus 2 would be the y-intercept if I kept going. So that's the equation that I use, 1x plus 2. But the domain for that specific piece, I mean, if I put like a little dashed line here, this piece of graph right here does not go past that domain value of x equals -1. So it's everything less than x equals -1, but nothing beyond -1. And the closed circle implies it's including that -1. So that domain restriction is for x values that are less than or equal to -1. Okay, now the second piece, and I'll use a different color, and I'll refer to this as graph number 2. This line right here, let's see if I can figure out the slope. So if I start here, it would go up 1 over 2, up 1 to the right 2, up 1 to the right 2, so the slope seems to be 1/2, right? And you can really see that the y-intercept is at -1/2. So let's just say, for the sake of worst case scenario, that you couldn't tell this was -1/2. It is very obvious that the slope is 1/2. So you could do point slope form and say, okay, y minus y1 equals slope, which is 1/2. You know what, I'm going to use a different color. That just doesn't seem to show up real well. So y minus y1 equals slope times x minus x1. Well then, I'm going to erase the y1 and x1 because I can pick out any point I want. So let's just make it easy, I guess. This point right here is 1, 0. So x is 1, y is 0. So that means it's going to be y equals, if I distribute that through, 1/2 x minus 1/2. And that's the equation of that line. So 1/2 x minus 1/2. So again, if you didn't know that that y-intercept was 1/2, because I might try to trick you, then use point slope form and figure it out. Now this line starts at -1 but doesn't include -1 because of the open circle, and then it's everything greater than -1. So its domain restriction is everything greater than -1. Okay, you try this one. So pause the video and see how you do writing the equations for this piecewise function. Okay, so it's obviously got two lines. One line would go like this. The other line is just a nice horizontal line. So I'm going to, again, start with this line. I guess I'll call it number 1. So the piece of that graph, if I look at the line, the slope is pretty clear that it's down 1 to the right one, down 1 to the right one, down 1 to the right one, so slope is -1. Very obvious that it's crossing through +1, so -1x plus 1. And that line, now notice where they meet is connected. So does that mean that they're both filled in circles? Well, no, because this line can't equal 2 and this line can't equal 2 at the same time, or that would not make it a function. So but you have no way of knowing. So let's just say that this line has the open circle. Okay, so then your boundary line, I guess, is kind of like x equals 1. Oops, no, it's not. Sorry about that. It's x equals 2. So this line is everything less than x equals 2. And I'll say that that includes 2. So everything less than or equal to 2. Okay, then the second line, and let's just call it line number 2, is just a nice horizontal line. Well, that's pretty easy because it's going at y equals -1. So y equals -1, and its restriction is everything greater than 2. So I write the domain x restriction as everything greater than 2, but not inclusive. And again, both of these functions couldn't include 2 because then you have kind of a, a contradiction there.